We came to know that Fermi energy EF for an intrinsic semiconductor lies exactly at the middle of the energy gap. And with respect to the extrinsic semiconductors, this Fermi level EF that is lying other than the middle of the semiconductor. That is, in case of n-type semiconductor, the EF is quite nearer to the conduction band, and in with respect to with respect to p-type semiconductor, this EF comes nearer to the valence band. That we have seen that the expressions we already introduced, Ne and NH. Ne refers to electron concentration, that is 4 root of 2 by h cube within the brackets pi me star kt 3 by 2, and the exponent of EF minus Eg by kt, that is for electron concentration, and the whole concentration, number of holes per unit volume in the valence band. It is given by the notation NH, that is expression for the electron concentration, and the whole concentration will get an will show that Fermi energy lies exactly at the middle of the energy gap for an intrinsic semiconductor. Once again, see the expressions for Ne, that is 4 root 2 by h cube. There is a smaller bracket and E exponent. So Ne and NH, these are the two expressions, Ne and NH. And now we are getting the expression for Fermi energy with respect to the intrinsic semiconductor. So for an intrinsic when you say intrinsic semiconductor, it is assumed to be the pure form of a semiconductor. So this is free from doping, germanium and silicon, if you imagine. And at room temperature or any temperature greater than 0 Kelvin, some electrons from the valence band get shifted to conduction band. You see that if you recollect the diagram, at any temperature T greater than 0 Kelvin, you see that the electrons from valence band they are moving into the conduction band, and that is at the conduction band you have certain few number of these electrons. They are also called free electrons or conduction electrons. If you count the number of electrons in the conduction band and if you count the number of holes in the valence band, it is almost the same, because the electrons that left the valence band, they are going and occupying some levels at the conduction band, isn't it? Therefore, here the movement of electrons that takes place from the topmost levels of valence band, and they won't occupy probably the bottommost levels of the conduction band. You don't see that the electrons from the bottommost, the lower levels, they are jumping into conduction. It is not so. It is the only the electrons that are much, that is with if you take the valence band, the electrons at the topmost levels of the valence band, they do take part and they goes to the conduction band. So since here the electrons from valence band, they are going to conduction band, so the only those electrons they leave the valence band, there creates a vacancy, and the electrons they occupy the conduction band. So they are exactly equal. So whichever the electrons that is left from valence band, they go and occupy the conduction band. Therefore, for an intrinsic semiconductor, the electron concentration, the electron and the hole concentration, if you look at, they are almost exactly equal. Ne refers to the electron concentration. So number of electrons they left per unit volume in the valence band, they are going to occupy the positions in the conduction band. So now it becomes there the number of electrons occupied. In the valence band, you will see the electrons left, and in the conduction band, you will see the electrons occupied. So the NH, the number of holes per unit volume, and Ne is the number of electrons per unit volume in the conduction band. So they are equal now. Therefore, Ne is equal to A. That is in this expression. Say I am using both equalities because number of electrons, the electron concentration is equal to the whole concentration. If you take that, it is Me star 3 by 2 EF minus Eg by kT. On the right hand side, MH star 3 by 2 E minus EF by kT. I told you that Me and MH, they are the effective masses. Me, effective mass of the electron, MH, the effective mass of the holes. So this effective mass can vary from fraction of m to more than that of M. So M can vary, that is less than M, 9.1 10 minus 31, and it is more than M also. So always the effective mass of electron or the hole, if you take the fraction, and then it's more than one, more than that. So we are using that. And if you simplify this equation further, so now again we are seeing that for all practical considerations, this Me is equal to Mh. Therefore, if you take that ratio of Mh by Me is almost equal to 1. It is the ln, natural log of ln by ln 1 becomes, therefore you don't have the first term, that is 3 by 4 kT ln Mh by Me. So you have only Eg by 2. Okay. So now that's how you can deduce the Fermi energy of with respect to an intrinsic semiconductor. It is nothing but the of the energy gap. Okay. We try to get the expression for electrical conductivity. So what is the expression for conductivity in a semiconductor? You know that a semiconductor, there the movement of electrons, as the electrons moves, it creates force in the valence band. That is there. You know that. So now if you imagine a semiconductor, the electron is moving. Okay. And in terms of valence band, when electron moves, means creates a conduction, holes. If suppose I told you that you cannot have always a 100% pure substance, there is small fraction of impurities will be always there. So this small fraction of impurity may be donating other minority charge carriers. The overall conductivity always we talk that is due to both the free electrons and as well as holes. So you know that the current I n times EVDA. Look at the expression I is equal to NEVEVDA. The overall product NEVDA gives you the current. So I give the current. Current is given by the number of charge carriers that have been crossing over an uniform cross sectional area with a certain velocity. So that is the current. So now it is told that in any semiconductor, the total current is always due to the sum of the charges due to the moment that is due to the electrons, and that is due to the holes as well. Therefore, now I split the current purely with respect to the electrons and purely with respect to the holes. So here, so if you consider only the electrons, then I is equal to NEEVEA. NEE, N with subscript E refers to the number of electrons. E is a charge on it. VE, V with subscript E refers to the velocity of the electron. A is the cross-sectional area. Similarly, current due to the holes IH is given by NH EVH into A. Okay, so this is the current expression, and now the total current is always due to the current due to the holes and current due to the electrons. So total current in a semiconductor is due to the sum of the currents due to the electron movements and the current due to the hole movements. Intrinsic semiconductor, because of the impurity, there may be some minor charge carriers also. So that is because of IH here. So therefore, the I is equal to IE plus IH, current due to electrons, current due to holes. So now we got the expression already that with respect to IE is equal to NE EVE A, and IH is equal to NH EVH and A. You have those expressions. Now you add those two according to satisfy this IE. So we take this is the expression I is equal to EA. If we take out EA as a common in this both the expressions, so within the brackets NEVE plus NHVH. We know that our aim is to find the electrical conductivity. So you know that electrical conductivity is given by the symbol sigma. How to get this sigma? You know that current density J is equal to I by A, that is equal to sigma times E. This is not true. So current density J, that is equal to I by A, that is equal to sigma times E. So making use of the above expression, that is I EA and divide, so sigma will get small e by e within the brackets NeVe plus NHVH. So conductivity right now given by small e by capital E NeVe plus NHVH. So now here one more the expression, I mean notation is introduced, that is mu here, mu subscript E and mu subscript H. This mu E and mu H represents the mobility of the electrons and holes. Now you substitute in place of E by E and VH by E into the above expression, you will get sigma is equal to E times within the brackets Ne mu E plus NH mu H. So this is the expression for electrical conductivity considering both the holes and the electrons. And you know that this is a general expression. Okay. For an intrinsic semiconductor, the electron concentration is equal to the hole concentration, therefore Ne is equal to NH. Since both are equal, I am introducing this equality by another term Ni, N with subscript I. Since both are same, so if you substitute Ni there, you will get conducted sigma is equal to E times Ni mu E and mu H. This is the expression for electrical conductivity for an intrinsic semiconductor. Okay. So now, what is the expression for the conductivity for an extrinsic semiconductor? In an n-type semiconductor, the electrons are the majority charge carriers. They are more in number. There are more electrons when compared to the holes. Therefore, electron concentration is more for n-type semiconductor compared to the hole concentration. Therefore, if you neglect the hole concentration NH, then I can write the electrical conductivity expression for n-type semiconductor as sigma n, that is equal to Ne, E and mu E. I am neglecting the E and other plus term of the bracket. Similarly, if you look at the, if you want the expression for electrical conductivity for a p-type semiconductor, that sigma p is equal to NH E mu H, because the electron hole concentration is more. So in p-type semiconductor, there are many such holes. A large number of holes will be there. Hence, the hole concentration is pretty large, too much compared to the electron concentration. Therefore, the conductivity due to this electron concentration can be neglected. So now here in a p-type semiconductor, the conductivity is mainly due to the hole concentration. Therefore, we got a sigma p is equal to NH E times mu H, where in the above expression, these expressions Ne and NH represent the electron, the concentrations and the hole concentration respectively. Okay.